Our first speaker is Dr. Mariana Figueiro, who is Light and Health Program Director at the Lighting Research Center and Professor at Rensselaer Polytech Institute. Her research concerns effects of light on human health, circadian photobiology, and the lighting for older adults.
Thank you. Can you hear me okay with the microphone? All right. In the interest of time, I'm just going to go into the presentation. The way I sketched the presentation was just talk about some key points, which hopefully will be basis for our discussion later on in this session. I do want to thank the organizers of the event for having me here. It's a pretty exciting day, so we're looking forward to it. All right, so let me start with the first key point, and I think the first one is we need to specify and measure the light stimulus as it affects the circadian system. As a lighting researcher, I have to admit that it gives me a little bit of chills when I see the American Medical Association putting out a report about the health effects of light at night, and there isn't really a single number there to characterize what light at night is. And I think if we're going to be talking about light at night, we need to specify the stimulus to try to then identify whether there is a problem or not. So in terms of trying to do that, obviously we don't know it all, and to your point, Fred, about blood pressure, at least we have a number, 120/80. It's something to start with, whether it's the right or wrong, at least we have something. So we do know from the spectral sensitivity of the circadian system, and here I'm just talking about acute melatonin suppression by light at night and phase shifting of the dim light melatonin onset. We do know that the circadian system is a blue sky detector. It has a peak sensitivity around 460 nanometers, unlike the visual system or reading black font on white paper, basically that has this spectral sensitivity, which is around 555 nanometers. So your lux meters, the ones that you use in your lab, looks at energy that falls under this curve, and this is how the circadian system responds to light, which is towards short wavelengths. Yesterday, Fred mentioned about the intrinsically photosensitive retinal ganglion cell, which is the major photoreceptor, but not the only one. The IPRGC does receive input from rods and cones, so all three classes of photoreceptors participate in how the retina converts light signals into neurosignals for the circadian system. In terms of absolute sensitivity, all these points are data that we gathered at the time we published this transfer function for all human studies on acute melatonin suppression by light at night. And here are sort of the light levels that you find at different sort of spaces, outdoors at night, all the way till outdoors during the daytime. And this would be what you have in office environment and around the home environment. And anything below 30 lux at vertical at the eye, and again, lux is not the right unit, but we always convert back to lux because people understand that. We didn't see any significant suppression from the studies that we've seen in the literature. Above 1,000 lux, you're probably close to saturation. So what you're talking about, the operating range would be around this range here. And people are really talking a lot about, LEDs and bluish white color lights and so on. And you do see about twice the effectiveness. So if you have the same amount of lux for an incandescent light source or for a daylight light source, which has more short wavelength content, you will see a little bit more suppression. Is about twice as much the effectiveness in terms of the suppression. But again, it's a starting point of thinking about spectral sensitivity and absolute sensitivity for the circadian system. In this case, it's in humans, and we need to now be able to translate also in animals, which I'll talk in a little bit. Now, it's not just about intensity and spectrum. Dose matters too. The curve that I showed in the previous slides, it's generally for 1 hour exposure. We did a study where we looked at the effects of iPads, and we did televisions, and we did computer screens. I'm just showing the iPads here. It was a 3-week experiment. They came in every week. 1 week they saw the iPad with these orange tinted glasses, which removes the short wavelength light. So that one was basically your sort of positive or your negative control. So we weren't expecting to see any suppression because you're not giving them blue light. Here we actually turn on the blue light. We gave them blue light goggles that was energized and giving them light, so we were expecting to see melatonin suppression in this condition. And here was the iPad at full brightness. What was interesting is we collected data after 1 hour exposure and after 2 hours exposure, and here are the melatonin concentrations. And we didn't see any significant suppression of melatonin concentrations with the tablet after 1 hour exposure, what we did see after 2 hours exposure. So again, it's not just the intensity and the spectrum, but how long you're being exposed to that light becomes important for us to define what that threshold would be. The other important thing, and again, dose matters, is I'm going to make a statement which will shock everybody, and then I'll go through it. Light through closed eyelids will suppress your melatonin. Like, really? Okay, so we did this study. We published 3 studies now where we developed a light mask. We are giving, actually, in this case, flashing light. We're flashing the light for 2 seconds every minute for 60 seconds, and we can see significant suppression. Now, we have to adjust the light to compensate for the eyelid transmittance. So we're talking about 50,000 lux at the eye in order to see an effect on the circadian system. That's outdoor light levels for you to be able to do that. The transmittance at short wavelengths through closed eyelids is less than 0.5%. So when you close your eyes, you need a lot more light to compensate for that transmittance. 1 second, the 2-second flash only once did not have an effect. We see an effect after a continuous flashing of light for an hour. One of the things we're learning too is that age matters. Of course, for those of us getting old, we do know it matters, but we're looking at the other end of the spectrum. We did this study with teenagers. They were about between 15 to 17 years of age, and we compared with college kids in their 20s. They were receiving the same amount of light at the eye. We measured with a calibrated device from self-luminous displays. The teenagers suppressed twice as much the melatonin. So it does seem like teenagers are more sensitive to light than older college kids, for example. And there's a study from Brown University, Dr. Carskadden and Crowley just published showing that kids in the 9-10-year-olds, pre-puberty, seem to be even more sensitive to light in the evening. So again, when we talk about individual differences, we have to take into account those different sensitivities when it comes to acute melatonin suppression. Now, the next part is the temporal part. Timing matters. The same light can be good at one time of the day, and it can be detrimental at other times of the day. So just talking about light without telling me when you're getting that light becomes probably not as useful, because we need to know when to get the light. We know from the phase response curve that morning light will help you go to bed earlier. Evening light will delay the time of your sleep. So we obviously are trying to avoid the evening light to try to minimize the delay of our sleep times. But studies that we're doing back in the lab are showing that if you want to be able to predict phase shifting of dim light melatonin onset using a mathematical model, you need to count all the light you're exposed throughout the day. Every photon counts. If you just take into account the morning and the evening light, you're not able to predict that phase shifting. So we have to take into account the entire light exposure in order to be able to see whether this is advancing, delaying, or even disrupting the circadian clock. So this is just a summary of the key point 1. We need to specify the stimulus and take into account all these different lighting characteristics in order for us to talk about the health effects of light at night. The second key point I want to make is that mice and humans are different. In case you didn't know, they actually are in terms of responding to light. I sometimes put that slide saying that mice and women are different, so that doesn't go very well, so I'll just put it in general humans. We do know that very low light levels of white light will suppress melatonin in rats, but we have to take into account that nocturnal rodents are generally several orders of magnitude more sensitive to light than humans. So when we're translating the work from mice to humans, we have to take that into account. So perhaps 5 lux of light for a mouse, it's very bright to the mouse, but it's not as bright to us humans. So here's just putting that sort of in a graphic format. This is the phototopic illuminance at the eye, and again, it's converted to lux to make it easier to understand, and this is just a relative response. And here is how you would read black fonts on white paper. If we're young, you can read a book under moonlight. Your visual system is extremely sensitive to light. So a night light will allow you to navigate in the space, go to the bathroom safely. It doesn't necessarily impact your circadian system. Here is a blue LED, a narrowband light source, which is a very effective light source for the circadian system. And here's the response in terms of acute melatonin suppression after 1 hour exposure. And here are 3 white light sources. This one has more short wavelength content, and this one has less short wavelength content. So this is more bluish white, and this is more incandescent light, okay? And this is how the estimated phase shifting responds to 30 minutes of light in a mouse. So you can see that the mouse circadian system is much more sensitive to light. So one of the things that we've been saying is perhaps we're giving too much light to a mouse in an animal lab, and we should be reconsidering lighting in animal labs to make it more biologically meaningful for them. The third point I want to make is that you need to use a calibrated instrument to measure light for the circadian system. There's been a lot of work, and I'm sure we're going to hear a little bit later on about the work looking at satellite photometry and self-reports of brightness and the link to breast cancer. I personally have a problem that no measurements of light at night were obtained inside the homes, but I think you can't have it all when you're doing these kinds of studies. But the question that we have is, are satellite images a good surrogate for measuring light at night as it impacts the circadian system, okay? And we don't think it is. And the reason is, this is what your satellite image is measuring. There's a lot of IR in it. So what people normally do, they use what they call the astronomical V-band filter, which is a filter here that filters all the IR. And it matches very closely to the photopic lumens efficiency function, which is what your light meters are measuring. But that is still not measuring the spectral sensitivity of the circadian system, which has a peak at short wavelengths. And more importantly, a lot of the street lights are high pressure sodium, which is that orangey type light, which has a lot of energy here. So you're probably overestimating light when you're using that kind of filter. And worse than that is that it's not necessarily reflecting what the circadian system is using. Now that we're starting to change to LEDs that have more short wavelength content, it would be interesting to start seeing those differences and how we measure that. So we have developed a calibrated light meter. This is, we call it dosimeter. You can use it at the eye, or you can use it as pendants or pins. And basically that has a spectral sensitivity that you can calculate circadian light for the circadian system. We use that in 72 teachers, school teachers that are very entrained people, very regular people. And they were the dosimeter, has personal sensors. We also use the calibrated meter at windows and at nightstands because we wanted to measure how much light they were getting in their bedrooms. And we compare that with the sky brightness from Cinzano et al., which uses that astronomical V-band filter. Okay, so it's measuring based on that. And what we found was that there was absolutely no relationship between the light that you receive in the window and in the nightstand with sky brightness. And it's not surprising. I mean, in a way, people will have shades, we'll pull the shades, and we won't see it. And because the V-band filter is not a good way to measure circadian light, we saw absolutely no relationship between these two. The next point I want to make is that you need to quantify circadian disruption in the field, not just light at night. Okay, and I think we've been talking about circadian disruption, but these are data from the Nurses' Health Study that we collected with Dr. Eva Schoenhammer. They were the dosimeters, and we looked at day shift and rotating shifts. There's a lot of overlap in terms of circadian light and an activity in this group. So if you want to be able to see the differences between these groups, you probably won't see it by only measuring the amount of light that they're being exposed to. So what we're proposing, we've been working with, it's a surrogate metric, which is not ideal, but it's one start point to measure circadian disruption in the field, which is looking at the correlation between rest, light and dark, circadian light and dark, and rest and activity patterns. So these are data for 7 days with day shift nurses, and these are rotating shift nurses. So the pictures already tell you they're very different in terms of their light exposure and activity exposure. So if you look at the cross correlation between light and dark and rest and activity, you get sort of functions like that. And with these functions, you can calculate what we call phasor magnitude. So a long magnitude means that you are active when there's circadian light and inactive when there's no circadian light. So it's a diurnal person, basically. And a rotating shift work has a much shorter phasor magnitude. So that's just one way of characterizing in the field if a person is entrained or disrupted. And we looked at the number of nights worked and the phasor magnitude, and we showed a relationship that as you increase the number of night works, which you probably are increasing the circadian disruption, you actually are reducing your phasor magnitude. So it might be sort of a good surrogate. Again, not ideal, but a starting point. Now, the other point I want to make is we talk a lot about light at night, but what about the light during the day? Are we just being exposed to too little light during the day? And we measured. We have circadian stimulus in the morning, which was the first 4 hours after people got up. If you look at a threshold of 0.1, which would be below here, we're very close to threshold in terms of morning light. So the question is, are we just underlighting our environments during the day and therefore the light at night becomes worse? We're doing some work with General Service Administration where we're collecting dosimeter data with office workers, and we're seeing a strong relationship between your circadian stimulus during the day and your phasor magnitude, which is that measure of entrainment. So the more light you get during the day, the more entrained you are. We're also looking that an increase in circadian light and circadian entrainment is associated with reduced self-reports of depression and stress. So, and they're sleeping better. So there might be an effect of light during the day on also how circadian disruption is affected. The last point I want to make is not just about blue light. This is a project we're doing actually with NIOSH. We've done a lot of lab studies where we show that red light, which does not affect melatonin, it's actually increasing objective and subjective measures of alertness, and it's reducing reaction time. So it might be that it could be a solution for shift workers like a cup of coffee. It helps them stay awake without necessarily disrupting their circadian system. We did the same studies during the day. We're actually seeing the same effect during the day. So I'm going to be passing out red light goggles after lunch so everybody is awake on their post-lunch dip. So just to summarize, we need to specify the stimulus, light level, spectrum, time and duration, spatial distribution, and photic history. Every photon counts. We need to take into account differences between humans and animals when translating the research. We need to measure total light exposures with calibrated devices. Need to measure circadian disruption in the field, not just talk about light at night. It's not just about blue light. And I want to leave a final thought. Could it be that light at night, even if it's not having a direct impact in people, is just an enabler for circadian disruption? We stay up late, we do things that we didn't used to do because we have the ability to do it. So there's sort of the social part that we need to talk about it. With that, I do want to thank the project sponsors. NIH has been very good with us on that, and you all for your attention.